Shh. We're going to continue on with physiology. Shh. Hey, what's up? We're going to continue on. Okay, so I mentioned I'm fallible, right? Very fallible. I actually goofed up on this slide. So when I mentioned colloids and crystalloids, these are actually all crystalloids. So honestly, I don't deal with plasma light very often. Maybe in surgery, I don't even know where they use it. I don't think we carry it over at Nemours. But these are technically still crystalloids. They actually have no protein-based products. What I was specifically thinking of are these colloids. These are ones that have things like albumin, either things like 5 or 25% albumin. You see in the bag here, and it's kind of yellow straw color to it, kind of indicative of the protein contained within. And then head of starch is another big one we use occasionally, like in the surgery realm. Okay, so these would be colloids because they contain proteins, versus the crystalloids, which are all on that last slide, only contain salts essentially. Any questions? Yes, ma'am.
So it's correct that colloids have protein and what you said, but just the table, those are all.
Yeah, those are all crystalloids. The thing here is that you'll notice that like these solutions will still be in things like sodium chloride. So the 6% head of starch, you notice here it's in 0.9% sodium chloride, which just says like normal saline. So even though it's kind of a mixture of the two, we still consider that a colloid because when you're administering it clinically, you're using it for that protein content, not necessarily for the salt content there, right? Okay, so continuing on. So we were talking about plasma tonicity. We said that if we have something that is an isotonic fluid being given, especially in comparison to the cells, we should really see no net flux of water in or out of the cell, right? It's isotonic, has the same osmolality, whichever you prefer. Going into a hypotonic solution, and what would be an example of a hypotonic solution? Water's a good one, right? Which we don't like to give directly intravenously to our patients. If you're looking at, if we say 0.9% sodium chloride is isotonic, hypo, or hyper. It's isotonic, right? It's normal saline. Say we did like 0.45%, right? That would be hyper or hypo. That'd be hypotonic. There's less solute in that fluid. So that would be hypotonic. That would cause water to go into the cells, which can be a good thing, can be a bad thing, depending on the situation. And then our hypertonic solution, so something like 3% saline, very concentrated concentration, a very concentrated solution there, that would cause water to leave the cells and cause that crenation or that kind of shrinking of the cells there, which can be useful if we have something like head trauma and we want to draw water out of the CNS, right? If we have intracranial pressure increases, we can draw fluid out that way. Okay. So looking at, as far as like transport, how we get solutes in and out of the cells, we've kind of alluded to this already back in pharmacodynamics, but there's a big comparison to make between the extracellular fluid and the intracellular fluid, and how you can kind of compare, contrast the electrolyte concentrations. You don't have to memorize this whole list, but at least be aware of some like kind of the big points we'll make about it. So for instance, look at the sodium concentration. Notice in the extracellular fluid, we have a lot more sodium than we do on the intracellular space, okay? That'll be important because when we have sodium channels on the cell open up, where do you think sodium is going to go? Into the cell, right? Because it's a higher concentration outside. It wants to go along its concentration gradient and get into the cell. On the flip side of that, we have potassium. Notice like your total body amount of potassium and sodium is essentially the same. It's just most of your potassium is going to be lying on the inside of the cell. So you notice here it's like 140 milliequivalents per liter. So it's pretty concentrated there. Notice out in the bloodstream, you may only measure, say, like 4 milliequivalents per liter. So not a ton that's out there, but that's important because we want to maintain that balance between salt and potassium, especially when we look at action potentials in just a second. Notice here calcium. You can see here the levels may be 2.4 milliequivalents per liter on the outside. Notice here on the inside, do you think that's all the calcium that lies within the cell? No, where does it like to hide out though? Yeah, so in the muscle will be the sarcoplasmic reticulum. There's also a lot in the endoplasmic reticulum. So because it's sequestered, and we mentioned that calcium is so important for cell signaling, it doesn't like to be out in high concentrations because you'd have too much signaling of different things you don't necessarily want at that time. But because we can keep it in the endoplasmic reticulum, it can be activated by things like that. We mentioned that IP3 come along and trigger the release of calcium to the cytoplasm. Those are big things to mention. Other things... There's things like cholesterol and lipids. Notice we have a lot higher concentrations in the cell. Why do you think that is? So we want to use that cholesterol and lipids in order to make things like cell membrane. We want to make, if we need to make new products and things like that, it can be more useful within the cell. And also notice the proteins. This is going to be important when we're talking about electronegativity and the kind of the stable anions within the cell. A lot of those are coming from the proteins there. So there's a lot more protein within the cell than is on the outside. Okay. So we mentioned transport. We can have either active or passive diffusion of things into the cell. Notice simple diffusion here can occur just going straight through the lipid bilayer, no problem, right? So things that are more lipophilic tend to cross this a little bit easier because they can cross that lipid bilayer. You can have things that go through just channels by themselves, and again, this would be along the concentration gradient. And then we have facilitated diffusion where things need a certain transporter in order to get it through, right? Again, this is still it's facilitated, but it's not necessarily an active transport, right? Because again, it's going to be going along the concentration gradient. No energy is used here. On the other hand, you can have energy being used for active transport, usually going through these carrier proteins. There's no such thing as like something active using energy to just go across the lipid bilayer. It's always going to be through some sort of carrier or transporter protein. Okay. So simple diffusion is important, especially for regulation of water and salt within the body. Usually this is regulated a lot by the hypothalamus. We see a lot of regulation of osmolarity of the bloodstream there. Essentially, the hypothalamus is going to be measuring the osmolarity of the bloodstream, and so it says, okay, well, let's say we have high plasma osmolality, right? Let's say like this is due to dehydration. We've had a lot of, say, sweating or vomiting or diarrhea. That's going to lead to the blood being more concentrated, and thus your osmolarity is going to go up, right? So what's that going to do to our bodies? The body is going to want to increase water intake. So this is where we can see things like antidiuretic hormone being utilized to help to retain more water within the kidneys. It can also be utilized to stimulate the thirst response. Now, this can go haywire in some cases. So, for instance, I remember running into this when I was in the surgical ICU when I rotated there as a fellow. Is that you'd have patients who have head injuries can occasionally have what we call syndrome of inappropriate antidiuretic hormone. Essentially, their brain, even though they're well hydrated, they're sending out too much antidiuretic hormone and stimulating that thirst response. And what's interesting is you've never seen anyone who wanted a drink of Gatorade so bad in your entire life, right? Because what's in Gatorade? Electrolytes, which plants crave, right? And then you also have a lot of water, right? So water and salt is what they want at that point because they have all these antidiuretic hormones stimulating thirst. I've never seen anyone lie, cheat, and steal in order to get Gatorade in their body before, right? They would get their family members to go sneaking Gatorade out of the cafeteria. They would try to sneak out of the room because they were so thirsty. But we had to restrict their water intake because otherwise they would end up having issues with diluting out the salt in their body, right? You get a hyponatremia from that. But it's very interesting just to having that kind of inappropriate thirst response being stimulated by something like a head injury, right? They're just sending out too much of this ADH. On the other hand, though, if you were to have the blood become too dilute due to having too much fluid, the body's going to respond to that as well by trying to excrete more water. And the best place to excrete water is? Urine. Yep, the urine. Yep. So the kidneys are going to be the best place in order to regulate that so we can excrete more water out of there and maintain our normal serum osmolarity, which we mentioned is anywhere between, like, say, like 280 to 300-ish in that range. That's where we want to keep things. Again, these get activated when you get kind of outside of that. You can notice here that there's kind of a downstream response that happens here where, like, you have dehydration, increased osmolarity. This is where those the hypothalamus is kind of detecting that, those osmoreceptors. And once they get activated, then that signal travels down to the posterior pituitary gland and increases ADH secretion, right? Notice we can have negative feedback loops as well that affect this. So, for instance, if the blood now becomes more dilute, now that we've got more fluid on board, it's going to shut down this process, right? So it's not going to be secreting any more antidiuretic hormone than we need, hopefully. Okay, some of the places where simple diffusion is very useful is going to be within the actual red blood cells and how they transport gases within the body. So if you're looking here at this top picture, this is going to be basically blood cells going out to the peripheral tissues, and here in the bottom picture is going to be where it's picking up oxygen over in the alveoli within the lungs. And this is useful because we're going to have simple simple passive diffusion of oxygen and carbon dioxide from the red blood cell to the outside of the cell. This is good because we can deliver oxygen to the tissues and pick up carbon dioxide, which is going to be a waste product of aerobic oxidative phosphorylation, as we mentioned in the last class. And then once it gets up into the lungs, it can release this carbon dioxide and pick up more oxygen and vice versa. Right.
Can you explain the difference again between simple diffusion and facilitated?
Yep, so simple diffusion is just something like kind of going straight through the membrane by itself, right? Facilitated means there's some sort of transporter that's involved, right? So we'll look at some examples of that in a second, but usually a protein within the membrane is allowing for the transport of that thing. But it's still passive because it's still going along its concentration gradient. There's no energy being expended, but it can't go across the membrane by itself. It has to have that kind of that facilitator there, that protein that allows it to flow through. So some sort of channel. Okay. Notice like we normally will keep a lot of that carbon dioxide is not necessarily stored strictly as carbon dioxide. We talked about that the enzyme carbonic anhydrase, which is able to keep it more in that bicarbonate buffer system, where it can utilize to help regulate the pH of the body as well. Right. So kind of multiple uses there, but mainly passive diffusion is allowing for this flux of carbon dioxide and oxygen within the tissues. Okay, so this will be our facilitated diffusion here, where again, it's not the ions themselves, because these are small charged molecules. They are very hydrophilic. They don't like to go through the lipid bilayer very easily. So things like sodium or potassium, they're going to need these channels in order to go through, right? So once these open up, they allow for flux of ions into the tissue, or depending on the concentration gradient. But this would be more of a facilitated diffusion, right? This is just an example. We still call it simple because it's non-active, non-energy using, but this is still considered a facilitated use of transport. Okay. Okay. So again, this facilitated diffusion, again, it's going to be net movement from high to low concentrations. Another good example of this would be glucose getting into the cells, right? Glucose can't cross the lipid bilayer by itself. By using these transporters, it does not require energy, but is allowing glucose to get into the cells through these proteins. And those transporters are going to be specific for that particular molecule, right? So you're not going to have things like steroids getting in through a glucose channel because it's kind of tailor-made to just affecting glucose there. Okay, so it's kind of further drilling down to the glucose example. Notice we'll have like different types of glucose transporters, which will actually be expressed in different types of tissues. So for instance, in the CNS, they like the GLUT1 transporter, which allows for glucose to cross the blood-brain barrier to get into the CNS. As you mentioned, the brain likes to use glucose as its primary energy source there. We have the GLUT2 transporters in the pancreas, and it's going to be monitoring blood sugar levels and secrete glucagon and insulin as needed. GLUT3 is going to be in the neurons, and then like GLUT4 is where you see a lot of use in the skeletal muscle tissues and the adipose tissues as well. So where you get a lot of that kind of peripheral uptake of glucose from the bloodstream is through these GLUT4 transporters. And again, what is kind of the trigger to opening up these channels? Yeah, insulin is going to be one of the main things. So it's kind of one of those kind of cofactors that helps to bind that receptor and allows it to open up and allow for glucose to flow through, right? So there's got to be some sort of trigger there in order for that to occur. An example of this, or to kind of illustrate this, you notice here like there's insulin receptors. They're going to be on the cell surface. These are actually tyrosine kinase receptors. All right, so we're again pulling different things from different classes here, but able to activate that, and that actually allows for better expression of these glucose transporters onto the cell surface, right? So if you have less insulin here, there's going to be less glucose getting out to the cell surface, or less transporters, and less glucose actually getting in the cell. Okay. And this is another good example. See the GLUT2. This is actually a good one where this is actually monitoring for release of. You have too much blood sugar around. This actually helps to regulate secretion of insulin by having glucose coming into the cell here. These GLUT2 transporters, you're able to have a metabolism of that, and we produce ATP, right? Because that's one of the major kind of products of glucose, and we're able to start to activate some of these channel receptors. We can allow for efflux of potassium and things like that, which eventually allows for calcium to come in. We say calcium is an important signal molecule. Once calcium gets in here, then it releases, causes these vesicles of insulin to be released out into the bloodstream. Right. So we'll get into more detail on these when we get to the endocrine section specifically, but these are good examples of how these can help with this facilitated diffusion. All right, active transport, one good example of this is going to be this calcium pump, where this is going to be moving things from areas of low concentration to areas of high concentration, right? I mentioned a lot of calcium within the cytoplasm is not free. It's mostly going to be within things like the sarcoplasmic or the endoplasmic reticulum. And so in order to get the calcium that's been released from those back into their spots that are being sequestered, that has to rely on active transport, right? And so you can see here we have something like normal kind of co-transporters. Sometimes you'll see certain transporters that will actually be flip-flopping different ions based on kind of what their concentrations are. But here we have one that sodium and calcium are kind of co-transporters here. And then you're having these calcium transporters, they're using energy in order to pump calcium outside of the cell. Okay, because again, if we have too much calcium in the cytoplasm, you're getting too much activation of different signals there. So we have active transport out of here, and then we can also have some active transport of calcium into the actual endoplasmic reticulum as well. That does require energy. Of course, once they're released, especially like in skeletal muscle tissue or something, we see calcium being signaling here with actin and the myosin. We'll get more into detail on that when we get to the muscle section. Okay. Again, calcium can also be useful for certain neurotransmitters being released. So here you have like acetylcholine being triggered by calcium in a lot of cases. Muscle contractions, all those are very useful with calcium. Okay. So again, you can have co-transporters that are working here. So there's something like sodium and calcium. They'll be, again, co-transported. And if you have alterations in concentrations of either of those, you can affect how well that transporter is going to function. So for instance, if I were to have a lack of calcium on the inside of the cell, this one's not going to be working to bring sodium in quite so much. You can have alterations that can occur. Certain drug effects can affect this. But just be aware that you have different co-transporters being affected by the actual concentrations of ions available. So a good example right here, this picture kind of showing this. If you have a large amount of calcium low amount of calcium here, you don't have a whole lot of transport happening, versus if you have a high amount of calcium, it's utilizing that ATP in order to spit it out, and it can bring some sodium back into the cell, but against the concentration gradient. All right. One of our favorite pumps is going to be the sodium potassium ATPase pump. This one absolutely requires energy. It's right there in the name, right? So if it says ATPase, it probably utilizes ATP, right? And we find this in all sorts of cells, but the main thing it does is help to regulate electronegativity of the membrane. Okay. Main thing this is going to do is going to shuttle 3 molecules of sodium outside of the cell and bring in 2 molecules of potassium. And it utilizes 1 ATP molecule when it does this. Okay, so again, sodium is on a higher concentration outside of the cell, shuttles it out. More potassium on the inside brings it in. Okay, against the concentration gradient, needs energy. So the big thing it's going to be doing here is resetting this resting membrane potential. You'll see when we have different action potentials that it allows for a lot of influx of sodium, a lot of efflux of potassium, long concentration gradients. This helps to get things back at baseline. I'll show you a picture of what that looks like in just a second. Again, just another picture kind of showing you exactly what's happening here. Even though sometimes you can have some passive release of things like potassium outside of the cell, mainly this is going to be one of the big things that helps to regulate this. So even if you have a defect of the sodium potassium ATPase pump, so if you have things like too much digoxin on board, this can be a problem here, and it can lead to things like arrhythmias if it's not working properly. Okay, so looking at membrane potential, normally you're going to find there's a lot more negative kind of anions that are within the cell than on the outside of the cell. Okay, so this leads to normally you're going to have kind of a more negative potential here on the inside of a cell versus on the outside. Okay, which is a good thing because we need that to help regulate our action potentials. Okay. And so one of the things we'll see is that by getting more sodium outside of the cell, that's going to lead to things being more positive, and getting potassium back in here, only 2 molecules of potassium for every 3 of sodium. This helps to regulate and make sure we have more negative on the inside of the cell than on the outside. Okay. That basically means if we were to measure this, normally you'll see a lot of cells will kind of rest at -70 to -90 millivolts. And then when you have an action potential, you see that will spike up very high, right? And so you guys covered like the cardiac action potential before? Anyone ever? Probably at least seen it before. We'll show you kind of what that looks like and how that negativity can be affected there. But again, the reason why we have a negative resting membrane potential is mainly because you have a lot of fixed anions, which are things like proteins and things like that have a negative charge on them within the cell. You have some potassium, right? Because again, the concentration of potassium there is pretty high, but you'll mainly have more positives on the outside of the cell than you will have on the inside. So we rest at a -70. Typically, you'll find that it differs a little bit based on the type of tissue we're dealing with. Okay, just another picture kind of showing you why we're saying mostly negative. Mostly is due to those fixed anions. And again, think about things like proteins. They can't really get out of the cell very easily, so they're going to be fixed there within the cell as long as that membrane is intact. Okay, so again, if you're looking at the concentration gradients, this is kind of a good picture to show you the comparison between the extracellular space versus intracellular. There's a lot more sodium, a lot more chloride on the outside here, a lot more potassium on the inside. These anions, though, those are the things that are going to be fixed within here. These are not going to be able to get outside of the cell very well. So if you think about it, if you have, say, a channel open up and you have a lot of chloride flow into here, is it going to be harder or easier to have an action potential? A lot more chloride flowing here, making this even more negative. Harder or easier to have an action potential? It's actually going to be harder. So this is where we're talking about those GABA channels. We're talking about GABA allowing chloride to flow in here. By making this even more negative, we're going to see that it actually has an even harder time having action potential. This is how we prevent things like seizures from happening. And I'll show you what that looks like in a second. Because again, every cell is going to have a certain potential it must reach in order to have an action potential occur. Okay, so just keep that in mind for right now. On the other hand, though, if we have other things where we have, like, say, hyperkalemia, which is, what is hyperkalemia? Yeah, increased potassium, right? So that means we have more potassium on the extracellular side in the bloodstream, right? And that can actually affect how this gets conducted as well. So one of the big things we worry about with hyperkalemic patients is arrhythmias, because it affects how action potentials are going to be conducted in the heart. Okay. So anywho, again, just look at these comparisons. Someone described cells as salt-wrapped bananas. That helps me to remember that there's a lot of potassium within the cells, and there's a lot of salt on the outside of the cells. Okay. I don't know if that's going to help you guys at all, but that helped me at least remember it a little bit. A salt-wrapped banana. So there's a lot of potassium within the cells, a lot of salt on the outside of the cells. Okay, sodium and chloride on the outside. Again, I have a lot of weird analogies, but it's how I make this thing work. So here's the action potential. This is kind of what I wanted to get to here. So note that you'll have some, especially like in the cardiac tissue, you're going to have some things that are able to generate action potentials on their own. But a lot of the cells do not do that, right? They're simply waiting for a certain trigger to come along, which is usually going to be influx of ions, right? So we're talking about those ion-gated channels back in pharmacodynamics. A lot of these are coming into play here as well. So essentially what you see is that we have a resting membrane potential. This here is about -70 for this potential for this particular cell. Okay, so sitting here at -70. Once it gets to a certain threshold, based on influx of ions, like positive ions, like sodium, you'll end up triggering this action potential here, right? So you have to get to a threshold, and then all of a sudden you can see a large spike as the action potential actually occurs. So sodium coming into the cell is the main thing that causes this positivity here, right? So once this gets up to positive 30, what does it do to the next cell in line? They have a really positive signal on this side of the cell. Now it can trigger that next cell, right? And then it can trigger the next cell. And that's how we have propagation of these action potentials, because one positive cell is going to initiate the next one, right? That's how we're going to have, when we look at our cardiac conduction, you'll see that much more clearly. But anywho, right here, you're going to notice that you're going to have a lot of sodium flowing into the cell. So you're going to see the membrane potential is going to increase until it actually gets a little positive, okay? Now, in order to get this back down, we can either we can shut down the sodium channels, right? So we have less positive cations flowing into the cell. That's one way we can do it. We can also start to release positive cations out of the cell as well. So this is where potassium efflux starts to happen. So again, we have sodium coming in here, sodium channels close, and now we have potassium leaving the cell, which is going to start to drive down our negativity. Okay. And we can actually get to a point here where we have this hyperpolarization, where it's actually even more negative than where we started. But what do you think is going to get us back to our reset point? Exactly. The sodium potassium ATPase pump is now going to come into play. It's going to start to kick more sodium outside of the cell, so it's getting rid of some of those positive. It's going to start bringing in some of the potassium, and then eventually it's going to kind of reset ourselves to get back to this resting membrane potential. Okay, so by resetting the sodium and the potassium concentrations, eventually we're going to get back to our resting membrane potential and getting our cell ready again to have another action potential later on. Everyone with me so far? Right, so if you did not have that sodium potassium ATPase pump, you'd end up having a case where you'd not be able to get back to a resting membrane potential. You may have too much hyperpolarization, and then that cell could not be potentially triggered, right? Or may need a stronger impulse to trigger that. So we want to have that pump working effectively. That's why we need energy for it to work in order to pump things against the concentration gradient to make sure maintain our normal homeostasis there, right? Our resting membrane potential. Everyone with me? Okay. More about that probably ad nauseum when we get to the cardiac section, but it's kind of an intro to that. Okay, so second messengers. Oh, we already covered this. This is so great. So now when I get to pharmacology, it's nice I'm doing physio because I already know you guys know this stuff because I already know I taught it to you. So now no blank faces are allowed when we get to pharmacology. Okay, that's the rule. So as mentioned, these second messengers are going to be super useful for initiating all sorts of biochemical processes here. Again, we mentioned adenylate cyclase being a big one. Working through these G proteins, once they get activated by whatever ligand, either endogenous or exogenous, binds that, it's going to lead to activation of G proteins. Then something like adenylate cyclase can then work. Okay. Again, these are going to be active processes for the cell signaling to happen here. So again, adenylate cyclase utilizes ATP, converts it directly over to cyclic AMP in this case, right? Or something like GTP gets converted over to cyclic GMP, right? That's all requiring those high phosphate energy bonds in order to be active. Okay. Again, I'm not going to go over this in super big detail since we already covered it, but essentially, remember there's going to be these different subunits that get activated. They're basically going to kind of break in half. Once that GDP has been replaced by GTP, they're active. They can have whatever effect they're going to have on either ion channels or downstream effects. But once that GTP, once that phosphate is cleaved off of that, then you're back at GDP, and it's going to recycle itself and go back to that kind of resting inactive state once again. Okay, and then another signal molecule can come in, bind the receptor, and then it starts over the process all over again. Okay, remember this is not just a one-to-one activation. You can have, say, like this alpha subunit. It can go and activate, say, 10 different receptors before it gets inactivated, or 100, right? Because we want to have this kind of cascade effect that occurs, where we can have one signal molecule activate several reactions. That way we get that kind of amplification effect that occurs there. So this is, again, not one-to-one. It can happen multiple times before it resets itself. Okay, just another picture kind of showing you what's happening here. Also, the beta and the gamma subunits can also have some effects as well. But again, they're also going to come back together in the inactive state, and GDP is going to be located there. Once you add that energy in and have GTP, that's when it starts to activate. Okay.
We need to know which subunits affect which effectors.
I'm not going to ask that. Yeah. But just know it's an energy-dependent process. Know what kind of second messengers it can affect, like adenylate cyclase. Know those protein kinases are really important for the other downstream effects that occur. You know, things like gene transcription or opening up, ion channels and things like that. So it's kind of what type of effects could occur due to this, receptor being bound and activated. Okay, so that's it for this section. Any questions? That we're all experts. We're going to continue to the endocrine section. So, objective, we're going to discuss endocrine. Okay, so we'll kind of go organ by organ. We'll do a little bit of a brief overview, and then we'll kind of go into the specific organs. We'll talk about what they normally do, and we'll also talk about what happens when they go a little wacky, right? So, some of the endocrine glands. So, we noted that our hormones, especially the endocrine glands, as opposed to like our exocrine glands, typically ductless, and they're going to be secreted within the blood, right? So they're going to be secreting into the bloodstream and affecting tissues all over the body as they travel throughout. And again, they only target tissues that are going to have receptors for those particular hormones. So, for instance, if you think about like estrogen, what type of organs would have estrogen receptors? It's like the ovaries. What else? The breast tissue, the cervix, right? So all those places have estrogen receptors, so they can respond to it, right? Some other places you might not think about having estrogen receptors includes the liver. The liver is responsible, as we'll see a little bit later, for producing clotting factors. So one of the big risks for when patients are taking estrogens is blood clots. Yeah, blood clots is a big thing. So if you ever see like a really young female patient who develops pulmonary embolism or DVT, one of the first questions you ask is, are you taking birth control, right? Because those estrogens, its effects on the liver, because it has receptors for it, can induce clotting factor production and induce clots. Okay, that's one of the big risk factors we worry about when you give like birth control or hormonal contraception to female patients. But, yes, ma'am?
Is that like with factor V leaving?
They probably have some interaction there. I've not actually delved too deep into that particular interaction, but yeah, those patients are always very difficult to manage as far as being hyper versus hypocoagulable and all of that. So they can be very difficult. I remember having a few during rotations when I was in school. We ran a Coumadin clinic. We had a patient with like factor V Leiden, and she was so difficult to get her INR in range just because she was just had not normal physiology for her. So it was pretty difficult. But yeah, so certainly that could come into play. Yep. So anywho, right, so your tissues have to have the receptors in order to be responsive to them, and they help to regulate lots of things. Talk about body metabolism, talk about growth, reproduction, all these can be affected by our hormones. So some of the major endocrine glands we'll talk about include things like our thyroid gland, also our parathyroids. We'll talk about the pancreas, the adrenal glands, the thyroid gland. Are these the only places where hormones can be secreted? No, you'll actually find that other like non-traditional kind of endocrine glands can also be secreting small amounts of certain hormones. These are just the kind of main manufacturing spots where these are being produced, though. So some other places we'll talk about include things like the intestines can produce some hormones. The kidneys are really responsible for regulating blood pressure, and so lots of hormones get made there, which can have lots of other effects. Vitamin D synthesis also is a big thing that happens in the kidneys. So lots of other places you may not necessarily think about being an endocrine gland can certainly have a role to play, and which we'll talk about those when we get those specific organ systems. But we're going to talk about the major endocrine glands here during this talk today. Okay, so hormones. I'm not looking forward to the day when my daughter has too many hormones. It's not going to be very fun. She's already bad enough as it is when it's nap time. She's way too cranky, but it's only going to get worse. Anyway, so we'll see that hormones, we can find some of them, these can be antagonistic, some of them are going to be synergistic, and some of them are going to be permissive, right? So if you hear antagonistic, what do you think of? Yeah, so we're going to think about things that are working against one another. Can you think of any examples like that? Yeah, insulin and glucagon is a really good example of that, right? Because one's trying to increase blood sugar, one's trying to drop blood sugar. And so that makes sense. Some will be synergistic, where they're kind of providing further support for one another and providing further more effects. We'll look at some examples of that. And then what do you think permissive means? Yeah, it kind of allows for, you kind of need one to beget the other. And you kind of, they allow for the effects to actually occur in the first place. We'll look at those examples. Other things you'll see, especially when looking at like antagonistic effects, looking at the interplay between calcium homeostasis gets very complicated because you're looking at things like calcitonin, you're looking at things like parathyroid hormone and vitamin D and all kinds of other products that come into play here in order to regulate how much calcium we absorb through the gut, how much of it gets deposited or taken out of the bones, and how much we get out in and out of the kidneys, right? So you can have lots of different kind of dynamic factors coming into play here. And obviously, if any of these organ systems go haywire, right? So if you have organ dysfunction in, say, like the kidneys, that can go out the window, and all of a sudden, you're having disease occur because of that. Another big one is going to be our blood pressure system, looking at angiotensin, looking at the renin-angiotensin system. We get to talk about hypertension. That's going to be very, very prominent here. And so those can have some antagonistic and also synergistic effects, right? So you can have things that not only constrict blood vessels, but also increase water retention, both of which can help to increase blood pressure, right? That would be a kind of a synergistic effect that you can see with your hormones. So I mentioned another good example of synergistic effects between hormones, it would be lactation, right? So two big hormones that come into play here is one's prolactin. Prolactin is really important for helping to stimulate the breast tissue and helps to develop that and gets the mammary cells ready to express milk. And then you also have, especially when the baby starts crying, you will have oxytocin being released as well, right? So prolactin and oxytocin have synergistic effects to allow for kind of let down of the milk and allow for the baby to be able to, or let the mom actually express the milk so the baby can feed, right? And so usually there's some kind of external response, usually like a kid's crying or something like that. So a good example of a synergistic effect there. You also mentioned, we're also talking about oxytocin being useful. Yeah, labor is the other big one. So you see oxytocin helping to kind of further develop things and allow for, because the baby's head pushing down on the cervix allows for oxytocin to be released and helps to kind of develop that further, right? So all these kind of synergistic type of effects occur in there. There's permissive effects. Can be a good example where, again, you have the target cells become more responsive when you have one hormone around, and it makes it more responsive to a secondary hormone. So, for instance, when you have estrogen around, that helps make the uterus more responsive to progesterone, which is kind of the sister molecule to estrogen. And then things like parathyroid hormone, PTH, that's going to be able to allow for the intestines to be more responsive to vitamin D, and that helps to increase calcium absorption from the GI tract, right? So again, these are permissive. They allow the tissue to become more sensitive to a secondary hormone. They're allowed to work a little bit better. And then we mentioned glucagon and insulin being our antagonistic hormones. Again, they're just doing the opposite effect here between increasing and decreasing blood sugar. Okay, so looking at hormone concentrations, you'll notice that different hormones will have different half-lives. What's a half-life mean, do you think? Yeah, so the time it takes to basically metabolize half of that hormone down. Some hormones you're going to see have very short half-lives. Some are going to have very long half-lives. So you're thinking about things like epinephrine. Do you want that to have like a really long half-life or a short half-life? Probably short, right? Because you don't want to be like in a super stressed, high sympathetic state for long periods of time. You have high blood pressure. You'd be feeling really crummy. Like you don't want that to happen. On the other hand, some things will last a long time, like thyroxine and your thyroid hormones. Like they stick around for a good long time, and that also will dictate how fast someone responds to those hormones, right? So things like thyroid hormone, when you're checking someone who's hypothyroid and you start them on a medication for that, you have to wait weeks before you can actually go back and test them again to see how they've kind of responded to it, because it takes time for the system to kind of regulate that when the half-lives are so long. We'll talk about steady state when we get to pharmacodynamics. That's essentially what we're trying to get to when we get to here. Most of the hormones, though, are going to be metabolized within the liver and then usually to less active products so they can be excreted or recycled, whatever happens to be. Okay, so tissues typically respond to hormones in a kind of predictable response when you're in the normal physiologic levels, right? So for instance, when you have normal amounts of things like luteinizing hormone and follicle stimulating hormone occurring in kind of this natural cycles within a female patient, like they're going to have their period and their menses kind of on a normal basis. When you start to get things outside of those ranges where you can start to either shut down some of these processes or help to enhance them and have them become, and in some cases you may find them become less specific. You may see them actually working at different tissues and you may not actually expect. For instance, if I were to give hormonal contraceptives, which usually contain an estrogen and a progestin to a patient, you'll notice that we're giving a lot higher concentrations than the body would normally be producing, right? And that makes sense because due to negative feedback loops, if I give a lot of estrogen and progestin, what does that do to kind of the upstream effects of like luteinizing hormone and follicle stimulating hormone? Does it enhance them or shut them down? Shuts them down. It's a negative feedback loop. I just mentioned that. So by shutting that down, you shut down the ovulation process, and that's hopefully how you prevent pregnancy from happening. But because I'm giving these drugs in higher concentrations than what are normal, you start to see these drugs affecting, or these hormones affecting tissues at other sites. And so this is why with progesterone you can see things like menorrhagia, and then also breast tenderness can happen there as well, right? There's kind of side effects that occur by going over the normal physiologic amount that would normally be released. Okay, so again, excess or too much or too little of these hormones can lead to negative effects in both directions. Okay, you can have a priming effect or kind of upregulation of receptors. In some cases, we've kind of mentioned this previously, but by having upregulation, you have more receptors available. That typically makes you more sensitive to the effects of whatever that hormone happens to be. This is actually an example of patients with kind of normal neurophysiology, and this is actual schizophrenia. So not hormone specifically, but it's still neurotransmission. An example here, we can have a serotonin neuron. So if you ever see 5-HT, that's shorthand for serotonin. Okay, so you have a serotonin neuron. If you have a normal functioning patient who does not have schizophrenia, they may only have, say, like one receptor here that gets activated normally, has whatever downstream effects. Some patients, though, they may have upregulation, and we're more sensitive to these effects of serotonin, and this is where it can lead to downstream effects like schizophrenia, where they have, they have some of these positive symptoms like hallucinations and things like that. But because you have more receptors and more sensitive to the effects of whatever ligand is around. Mentioned the desensitization. Usually in response to hormones and things like that, you're going to have receptors be expressed less frequently. Here you can see where one of these desensitized receptors gets basically integrated into an endosome, and then it can combine with the lysosome and further metabolize that and get rid of it, right? So if you want to upregulate, you're going to have increased synthesis of receptors going to the cell surface or wherever the receptor's at. Downregulation, you usually have those either being recycled or just metabolized. Okay, so getting into our specific endocrine glands. So these are some of the major ones we're going to talk about today, at least to some degree. Some of these we might not cover in a lot of detail, but some of the major ones. So some areas you might not necessarily think about being a hormone gland, so things like the heart, right? So you can see atrial natriuretic hormone actually is released here, and it's important because it actually can be released in response to kind of the stretch in the atria, right? So if you change that, if you have someone like congestive heart failure or something, that ends up going to the kidneys. Kidneys say, hey, we need more volume in the body, and it's going to lead to, it says, hey, we have too much pressure in the atria. It says, hey, let's get rid of some of this extra water and sodium through the kidneys, right? So these are some examples of things we'll talk about. You don't have to memorize this list specifically, but this is a good thing to refer back to when we get to the specific ones we'll talk about in the upcoming slides. Okay. So if I don't talk about it specifically in the upcoming slides here, just know that I'm probably not going to pull directly out of that table, but it's a good review. Okay, some other things we can run into, things like the parathyroid glands, pineal glands, all that. We'll talk about these more in detail as we move forward. Okay, so the first one I'll talk about is the pituitary gland. So we're looking at specifically where the pituitary is going to lie. Where do you guys think it's at? Within the brain, yep. Put a big picture of a brain. Probably. You're like, this is not anatomy. I don't need to know specifically where it's at, right? Wrong. We're still going to talk a little bit about it. All right. So, anyways, here's a pituitary here. Notice how it's kind of lying, where it's at in kind of relation to the hypothalamus, right? Hypothalamus and the pituitary gland are going to be very, very important kind of cousins to one another. They're going to be each are going to be very responsive in releasing a lot of these hormones, or not releasing hormones as the negative feedback loops get activated. So there's a very tight relationship between those. Anywho, we'll talk about the anterior pituitary and what that's going to be releasing versus the posterior pituitary. This we're going to have a few different hormones they're going to be releasing, so it's important to know which ones come from the anterior versus the posterior, how that can affect the patient. One of the interesting things that I never thought about, you guys know any famous schools that are in St. Augustine, Florida? There's a lot, yeah, but what's like the really famous one? Like for kids with like disabilities. Yeah, School for the Deaf and Blind. That's where Ray Charles actually went to school at for a period of time. I think either Ray Charles or Stevie Wonder. I think it was Ray Charles, though. Anywho, they had the School for the Deaf and Blind there. And so actually I got an opportunity when I was in school. We did like a brown bag event where we actually got to go during their intake. When they were about to start school for the semester, we actually go and look through all their medications, make sure everything, make sure the med list is up to date, make sure all the drugs are there, and it's, they're not, grody or anything like that. And so what I never realized is that a lot of these kids, they end up developing blindness secondary to cancer. And one of the things that cancer will end up doing is they end up losing their, when they have a resection there, they end up losing their pituitary gland, right? And so you notice that like a lot of the hormones we're going to be giving, or we're talking about here, we're having to give these patients. So things like growth hormone, things like thyroid hormone, because you're going to realize they're going to lose a lot of function when they don't have this pituitary gland here to release a lot of these kind of trophic hormones, okay? Just know this is really, really important for helping to lead to further downstream secretion of a lot of hormones. If you lose this, you have to replace all of that, right? Because your body's not going to have those signals to produce it on its own. So we'll look at those specific examples as we go forward. Okay. Just notice the kind of close approximation between the hypothalamus and the pituitary. Very close communication happens between these two, and you're going to see that usually the hypothalamus is kind of the initiator for a lot of the secretion of different hormones. Pituitary is going to lead down to a secondary release of some sort of hormone to stimulate the final product from being made. We'll look at those examples in a minute. Okay, so the anterior pituitary. So some of the things that can be released from these, and again, be familiar with these and kind of what the different steps in the process of release of these hormones are. But we have things like corticotropin releasing hormone. Okay, so this is going to be released from the hypothalamus, right? So we have all this line here is going to be all the hypothalamus, and what they're going to be secreting. Next, you're going to have the anterior pituitary, and then finally the end organs where those are going to be eventually expressed from. So we're going to start out with, at least with our stress hormones, things like corticotropin releasing hormone come from the hypothalamus. It's going to be releasing ACTH, or adrenocorticotropic hormone, and that'll be affecting our adrenal glands. Okay, this is where we're going to see a lot of things like our corticosteroids and also our mineralocorticoids come from. You guys heard that term, mineralocorticoids? Or glucocorticoids? You're going to be intimately familiar with them in a little bit. But they're really, really important for blood pressure control, also our stress response, immune system. Huge, huge things happen here with our corticosteroids. You can also have thyrotropin releasing hormone, or TRH, that gets released by the hypothalamus into the pituitary. Here we're going to have thyroid stimulating hormone, or TSH. This is really important when we're monitoring for effects of thyroid medication to see how a patient's responding to it. If their level's too high or too low, that tells us kind of if they need to be replaced or they need the dose reduced some. It's going to be affecting the thyroid. Main thing we're going to be seeing here is T4 and T3, which are going to be our main thyroid hormones, and also calcitonin, which will be important for kind of bone homeostasis. Next, you have your gonadotropin releasing hormone, and also you'll have an inhibiting hormone as well. So again, one will be more stimulatory, one's more inhibitory, and that will affect luteinizing hormone and follicle stimulating hormone. Note that both men and females are going to be producing both of these, although the end products that they make are going to be different, right? So females are primarily going to be producing a lot of estrogens and progestins. They still produce some testosterone and other androgens, but the males are mostly going to be making testosterone and other androgens from that, from the testes. Next, we're going to have prolactin releasing peptide. There's also a prolactin inhibiting factor. A lot of this is regulated through dopamine as well, and we'll see when we get to like schizophrenics who have issues with dopamine. You're going to see they have a lot of prolactin problems here. But basically, it'll stimulate the anterior pituitary or inhibit it to release prolactin. We mentioned that's really important for things like development of the mammary tissue, allowing for breast development and allowing for expression of milk. And then we'll talk about somatocrinin and also somatostatin. These are going to be growth hormone releasing hormone, and then also growth hormone inhibitory hormone. And that will allow for growth hormone to be excreted from the anterior pituitary. So these are main anterior pituitary hormones that are going to be released in order to affect the kind of end organs. Okay. Everyone with me so far? Everyone's ready for a nap? It's okay. Oh, maybe we get some increased adrenal cortex activity here. Maybe get some more. No, okay. We'll talk about melatonin later. That's probably what you guys are experiencing a lot of. That's okay. This is another good table, just kind of listing out what the hypothalamus hormones are going to be, what the anterior pituitary hormones are, and our target organ, and then finally what the function is going to be. So you can kind of refer back to this as kind of a cheat sheet for our different organs we're going to be talking about specifically. So we were talking about basic hypothalamic control of the anterior pituitary. Just note that the hypothalamus is going to be releasing a lot of these releasing hormones. So if you see the RH at the end of there, that's usually what's going to be. Just note that the few exceptions there where there are some inhibiting hormones as well. So the gonadotropin inhibiting hormone, the prolactin inhibiting hormone, also the somatostatin, which is growth hormone inhibiting hormone. Somatostatin is one we use pretty frequently actually in clinical medicine. Another name for it is octreotide. Which is actually I'm trying to think of the word. Not stimulated. It's basically it's a trying to think of the word. Synthetic. There you go. Synthetic form of somatostatin. We actually use it a lot for things like GI bleeds, and sometimes we use it for a couple of different overdoses. But anywho, right. So somatostatin is going to be this growth hormone inhibiting hormone. After you talk for this long, you end up losing easy words, so it'll continue, I'm sure. Note here, we mentioned the substances will be released by the anterior lobe of the pituitary gland, and then also the major ones coming from the posterior is going to include our antidiuretic hormone, or vasopressin, ADH, and then also oxytocin, right? So we already kind of alluded to these previously, but we'll talk about them in more detail in just a few minutes. Okay. Okay, so then it's good to note the kind of the pathway for these hormones and how they get released and where they're being released from. So things like adrenal corticotropic hormone that's being released to stimulate corticotropin releasing hormone, cortisol releasing hormone. So just in order to keep the pathways straight there to make sure you kind of know the order in which they're coming from the hypothalamus to the pituitary to whatever end organ they happen to be going to, right? But we'll get into more of these details in just a second. So the first one we'll talk about is growth hormone. So what do we think growth hormone does? Helps you grow, absolutely. Yeah. So basically, the hypothalamus helps to secrete somatostatin, which will be growth hormone inhibiting hormone, and then also the anterior pituitary helps to secrete actual growth hormone itself, right? So it's not necessarily an end organ that is further releasing any hormone. Kind of growth hormone is the kind of the business molecule itself. Also have the hypothalamus secreting growth hormone releasing hormones. That's going to be kind of the more stimulatory effect there. So what kind of tissues do you think this helps to develop? Bone. Bone's a good one, right? So helps develop the bone. Muscles, another big one. Who abuses growth hormone? Yeah, sometimes athletes will do it because it helps to develop the muscular tissue. It also works on lots of other types of tissue. So I was going to put a picture here. It was kind of gross. But if you ever see like bodybuilders, if you ever look up growth hormone gut, one of the things it actually does is it will stimulate muscles to grow, but also things like your liver and your intestines and all those things. And so these just massive, like just look almost like they're pregnant or something. These big muscular guys. So if you ever Google, maybe search off for that one. I'm just kidding. But yeah, so they'll sometimes abuse that in order to get bigger muscles. You also will find that the release of this is going to be in conjunction with things like sleep and also with strenuous exercise. So if you were to look at the release of growth hormone throughout the day, notice it has kind of different peaks and valleys. Normally strenuous exercise will help to stimulate a lot of release of growth hormone, but the other big thing is going to be sleep, which is why I tell you if you're trying to put on muscle, get lots of sleep, because that's when your brain's naturally trying to secrete most of the growth hormone throughout the night. Okay, and if you were to look at body weight, say if you were to inject someone with either no growth hormone, they just had what they naturally release, versus someone who's getting extra growth hormone, you can see that the actual weight will go up pretty significantly because all those tissues are starting to hypertrophy, right? And if you see some derangements in this, either you have too much growth hormone. This is where you can see issues with gigantism. Right, so you can have very large individuals get very, very tall, and then also if you are deficient in growth hormone, you can have dwarfism, right? So you can have very short stature, and you notice that when I was mentioning those kids at the school for the deaf and blind, a lot of them were on human growth hormone because they had that pituitary resected throughout the, for their treatment was usually for cancer, and then a lot of them would have to have supplemental growth hormone because again, most of them were either young children or teenagers who were still developing, right? They're still growing, so they need extra growth hormone exogenously being given in order to make sure they achieve their kind of normal stature for whatever they would have been normally, right? Next we'll have prolactin. Pretty obvious what it's going to be doing here is helps to develop this breast tissue, mainly the mammary glands, and then we'll end up seeing that actually, like another thing prolactin does is actually inhibits ovulation, right? Because if you are actively trying to feed a young infant, do you necessarily want to get pregnant again? Biologically, you probably don't, right? Because you're trying to give the excess calories and things like that over to your infant. You don't necessarily want to be developing another human body. So normally prolactin is a very good way to prevent pregnancy early on, unless you're my wife and then she gets pregnant again. That's okay. It took a couple months. Her prolactin was probably starting to drift down a little bit. But so come Christmas Day, we got another one on the way. My mom said she'd name her Holly, but I said Hollywood would not be a good name for a baby. You made fun of the rest of her life. No good. All right. Right. So anyway, so naturally, what's occurring though is that once the pregnancy has occurred, the baby's born, prolactin is going to be in high levels, and that will actually end up leading to the expression of the breast milk and whatnot. You'll find that in some patients they will have if they have either like a prolactinoma, where they're releasing too much prolactin, or if they are in a kind of a hypersecretory state, that actually helps to block ovulation unnaturally. So, for instance, one of our friends, she's unable to get pregnant right now because she's having excess prolactin, which actually is inhibiting the ovulation process. So there's certain drugs we can give to prevent that, but it can be one of those things that either comes about either due to some sort of tumor or some other kind of physiologic process that can block that. So again, you'll have prolactin, which is going to be stimulatory for expressing milk. You also have a prolactin inhibiting hormone, which can also block some of these effects as well. Prolactin in males is still somewhat useful. It helps to support the effects of luteinizing hormone and follicle stimulating hormone, which we mentioned in a few slides, as being kind of stimulatory on the gonads. And it also can have some effects on regulating water balance and electrolyte balance. So you can end up seeing kind of holding on to a little bit too much fluid if you have kind of high prolactin levels.
It would do that in females as well, though, wouldn't it?
It has those effects as well, yeah. So it helps the luteinizing hormone, just to show that you still have some effects in men. Men are still going to produce prolactin to some degree, and actually in some cases, I mentioned dopamine is really important for prolactin expression. One of the things it runs into, especially with drugs that block dopamine effects, you can have too much prolactin effects, and so this can lead to things like gynecomastia in men, right? So men that have too much prolactin can develop enlarged breast tissue, essentially. So again, looking at things like prolactin is going to be an increase. It gets kind of stimulated by things like suckling or the baby crying, things like that. And again, it'll have that kind of synergistic effects like oxytocin to help release both the production of actual milk, and oxytocin helps with the actual release of it itself, kind of the letdown of the milk that occurs there. Okay, so continuing on with kind of more sex hormones, we have the follicle stimulating hormone and luteinizing hormone. So these end up getting stimulated by the hypothalamus with this gonadotropin releasing hormone, and this will have stimulatory effects on the anterior pituitary to release LH and FSH, right? So this is really important for regulating the menstrual cycle for females. This will also help to stimulate androgen production or testosterone, specifically in male patients. Notice here you're also going to have negative feedback loops that are happening here. So for instance, if I were to give a female patient high doses of estrogen and progesterone, that's going to feed back here and shut down this GnRH secretion, also inhibit this LH and FSH, and you would have no ovulation, right? So it would lead to no periods, and you would also not be able to get pregnant, hopefully, if you're taking it correctly. On the other hand, here you can also have issues where if you were to give exogenous testosterone, right? So if you have male patients who maybe are taking this when they don't necessarily need it to, another, kind of similar to growth hormone, they can abuse this for developing muscle tissue and things like that. That can also have a negative feedback loop here, where you're actually decreasing release of both GnRH and also LH and FSH. And so one of the things they say, like if you take too much testosterone, what happens to the testicles? They shrink, right? Because they're not receiving that stimulation from LH and FSH, and so the tissue is like, well, I have enough exogenous testosterone around, I don't have to develop this tissue at all. So they end up kind of shrinking some. So that's one of the things you'll see. So it's kind of a common side effect for administering testosterone, either legitimately or illegitimately. Again, just we can also give synthetic growth gonadotropin releasing hormone occasionally, and this actually can be useful in shutting down this whole process here. So for instance, if you had a patient who, for instance, had an issue like, say, breast cancer, right? And so you want to decrease the actual production of estrogens, because estrogen has positive effects on the breast tissue. You could actually give something that shuts down this whole process, like giving something like gonadotropin releasing hormone. Would have a negative feedback effect here, and you shut this whole process down and have a very little estrogen production actually happen there. Okay, so there's lots of ways we can kind of play with this with medications to affect these negative feedback loops to prevent production for a lot of these different substances, right? So we kind of lots of ways to kind of play with this. And notice that the nice thing here is there's two steps where this is feeding back. So not only are we inhibiting, say for instance, once we have enough either androgens or estrogens or progesterones, that's both going to inhibit both the hypothalamus and the anterior pituitary. Okay, so it's kind of multiple steps where it's being inhibited. There's also multiple steps where this can go wrong, right? So for instance, if you had a problem with the hypothalamus, it doesn't matter how well functioning your anterior pituitary is, if it doesn't have that GnRH, it's never going to be stimulated, right? So you'd still have the same effects as if you remove the pituitary gland. You still would have no stimulation on the gonads, right? Okay, so moving on. Next we have the adrenal gland. Where are those at? Right atop the kidney. All right. Right, so these are going to be retroperitoneal, found atop the kidneys, and they're going to be consisting mainly of an outer adrenal cortex, and then you're going to have this inner adrenal medulla, right? So they're going to be functioning as basically separate glands, and we'll kind of differentiate their processes here based on the tissue type. Basically, the medulla here is going to be secreting epinephrine and norepinephrine, which is going to be important for what type of responses? Yeah, fight or flight, right? So this is going to be our stress responses in a lot of cases. And then you're going to find that the adrenal cortex is going to be secreting steroids in response to ACTH, or the adrenal corticotropin hormone there. So essentially you'll find there's also 3 layers of that, and we'll see some of the different effects and where those are going to be secreted from. But the zona glomerulosa, zona fasciculata, and the zona reticularis are the 3 main spots where you see tissue hormones being released there. So just going to give you a kind of more pictorial example of how kind of a cross section of the adrenal gland and how those tissues are kind of being signified there. Okay, so what's typically happening is you're going to have the hypothalamus secreting its corticotropin releasing hormone, which will end up going over to the anterior pituitary. Okay, then that's going to stimulate release of adrenal corticotropin hormone that goes to the adrenal cortex itself. So what happens when you get here is that it's going to be stimulating release of both cortisol. Cortisol is also mentioned as another name for it would be hydrocortisone. We're giving kind of exogenous cortisol, would be considered hydrocortisone. So that's a glucocorticoid. Talk about what that means in a second. You have aldosterone, which is going to be a mineralocorticoid. And then we're going to have small amounts of some androgens. So this is clinically not super significant for us. We're going to be mainly focusing on the glucocorticoid and the mineralocorticoid effects here. Okay. And again, you can have negative feedback loops at either at the hypothalamus or at the anterior pituitary in order to shut down or inhibit production of these different hormones, right? The different steroids. So a good example of this would be something like, say, for instance, you have stress. This is going to stimulate the CRH from the hypothalamus, which will end up secreting more ACTH down onto the adrenal gland, right? So this can have positive effects for increasing like blood pressure, which is going to be sensed by things like the kidneys. So once that happens, it's going to cause negative feedback and shut down further production up in at the hypothalamus and at the pituitary. So we'll look in more detail on what that is, but just know that there's also negative feedback loops here regulating this as well. So looking at some of the secreted hormones here, you're going to see that aldosterone, which is going to be a primary mineralocorticoid, is going to be coming from the zona glomerulosa. And this is really, really important for regulating blood volume and also electrolytes, namely things like sodium and potassium. So mainly working within the kidneys to try to help to hold on to more fluid and to more salt. Okay. You're going to find cortisol, which is going to be our glucocorticoids, is going to be coming from that zona fasciculata, and it's going to be regulating glucose metabolism, right? So if you're in a really stressed out state, do you want to have more blood sugar around or less blood sugar? So like a bear hops out at you, you got to run away. You want more blood sugar, right? So you'll find that the glucocorticoids are going to be positive for stimulating or releasing more blood sugar into the, having more blood sugar in the bloodstream in order to utilize that for energy, okay? Often you're going to see that these can have some negative effects because, again, these can overwhelm kind of the normal processes in the body. So if we're giving something like, glucocorticoid exogenously, you can see that can run into problems where if they have like diabetes, they already have too much blood sugar, this can worsen that, right? So we can overwhelm these kind of natural homeostatic processes here. But again, look at the different tissue sections here. But the zona fasciculata is going to be where the glucocorticoids are coming from. There's a few other ones, but cortisol is going to be the primary one we're going to look at. And then the zona glomerulosa, where we're going to see mostly aldosterone. And then finally in the medulla, you're going to have epinephrine and norepinephrine mainly being released from there. Okay. We're not really worried about these androgens here, because clinically they don't really come up all that often. Okay, so looking at cortisol specifically, let's look at some of the more detailed here. So looking at these hormones, we can see that most of them are going to retain kind of the same structure here, and a lot of them are actually being derived from cholesterol. Right, so the cholesterol we take in through our diet or we're producing within the liver can be changed and modified into all sorts of different hormones, right? So including with that, we can see things like progesterone gets made here. We see things like cortisol being made here. Aldosterone also gets made in this process, and notice they all kind of have very similar structures to one another. This is important, especially when we get to pharmacology, because you're going to find that when we're giving exogenous steroids, based on the structure, they can have some bleed over effects to where, like, for instance, if I give progesterones to a lady for oral contraception, one of the things you can see is that some of them are going to have these mineralocorticoid effects, right? That can lead to fluid retention and lead to edema happening, right? You can sometimes see where, for instance, if I'm giving, let's say if I'm giving cortisol, it can also have some effects on blood pressure and retaining more fluid. So there's some bleed over effects here. And you're going to find that not all of them are going to be 100% specific for glucocorticoid receptors or mineralocorticoid receptors. There's a little bit of interplay there because the structures are so similar. Okay, androgens also end up coming from here. So things like testosterone is also made from the same kind of process. So just memorize this whole thing here, all the enzymes, and I'm just kidding, don't do that. I was trying to stimulate your fight or flight response for a second there to wake you up, but anywho, so again, looking at zona glomerulosa is where aldosterone or mineralocorticoids are mainly going to be coming from. Again, this is the primary mover and shaker within the kidneys, retaining more water, holding on to more salt, and actually excreting more potassium. Okay, so it gets rid of potassium, holds on to sodium, holds on to water. So what do you think this does to blood pressure? Should increase it, right? So the more volume that you have in your the vasculature, the higher the pressure is going to be, right? And then looking at the glucocorticoids, this is going to have positive effects on gluconeogenesis, increasing our blood glucose. This will also lead to some retention of water, and a lot of that's related to its interplay and having some activity at the mineralocorticoid receptors. Also, one of the big things we like it for is anti-inflammatory effects. So this is where we get a lot of our effects. If you have an infection and your body's like in a really stressed state, you're releasing a lot of cortisol, right? Or if you have an injury, something like that, you're releasing these glucocorticoids to deal with some of that inflammation that's happening there. So this is also why if you have too much inflammation happening, we also give you exogenous steroids, exogenous glucocorticoids in order to help deal with that, right? To tamp down the immune system. And then you mentioned the androgens there. So looking at the actual process here, so again, if you have just kind of non-specific stress, what's going on here, the hypothalamus releases that CRH, anterior pituitary is going to release that ACTH, and then that will stimulate the adrenal cortex. Cortisol levels are going to go up, and that typically will end up shutting down further production of these steroids. This is really important when you have patients who are on steroids for a long period of time, right? So for instance, if I were to give you, say, a good one's prednisone. You guys ever heard of prednisone? Prednisone is a glucocorticoid. We use it for things like asthma exacerbations. We'll use it for things like rheumatoid arthritis, all kinds of different things. If I were to give you prednisone for, say, a month straight, okay, so what's going to happen to this negative feedback loop? It's going to shut it down, make it more stimulated. Should shut it down, right? So if I have too much cortisol here, or a drug that's like cortisol, like prednisone, you end up activating that negative feedback loop, right? So that means your adrenal glands are not really secreting a lot of its own cortisol because it's getting exogenous stuff, right? It thinks, okay, well, I don't really need to make a whole lot because I have enough around already. So if I were to take you off of that steroid immediately, How long does it take, do you think, the adrenal gland to really kick back into production? Is it like immediate, or does it take a couple days? It takes some time. Yeah, it takes at least a few days in order for it to really get stimulated again, because this is not a super quick process here. What that means is if you have a patient who you're on, say, high-dose steroids for a long period of time, and you cut them off cold turkey, they can go into adrenal insufficiency, which means they can't regulate their blood pressure very well, they can't regulate their blood sugar very well. It can be potentially life-threatening, which is why you always see patients who are on long-term steroids, they recommend a taper to come off of it. Or has anyone ever taken, you don't have to actually raise your hand or anything, but have you ever been on methylprednisolone dose pack? You guys ever seen those packages? How they have a bunch of pills you take on the first day, and you take a little one less pill each subsequent day until you're off. That's a built-in taper, so that way you don't really run into this issue. Okay, so by tapering down your dose over a period of time, you allow the adrenal glands to start to slowly kick back into production. That way, when you cut off the steroid, you're back at your normal baseline. Okay, so that's one of the things we run into, where you want to make sure that you build in these tapers and don't cut someone off cold turkey if they've been on it, say, like more than a week or so. So again, normally when you have some sort of metabolic or cardiovascular change, so say like you have a drop in blood pressure or something like that, this is going to be stressful stimulations that will end up triggering the hypothalamus to release that CRH. And again, we kind of looked at this process here. You can notice, like, it can kind of get out of control, especially when you have cortisol being an anti-inflammatory. If that prevents your body from fighting an infection, the infection gets even worse. That causes more stress, and that releases more cortisol. And so you can find issues where this is not necessarily a perfect system and kind of get overwhelmed by itself over a period of time. If you have kind of too strong of an, usually like an inflammatory process. You see this a lot as well with patients who are especially like night shift, people who work in a night shift, they oftentimes have higher cortisol levels because of the fact that their body's in kind of in a stress state, because you're awake when you should be sleeping, and sleeping when you should be awake, right? And so that can put stress on the body over time. That can lead to things like weight gain due to these glucocorticoid effects you can see there. Okay, so again, this all kind of comes into play, and you'll see it pop up again and again in lots of different patients. So I mentioned some of the things we'll see when you have those glucocorticoid effects. And again, these are working intracellularly, working at the site of the nucleus to change gene transcription, right? So it's affecting protein transcription and different things like that. But essentially what we're seeing is that you're going to have increased blood glucose levels. So again, think about if you had a diabetic patient, and they're in a stress state, their blood sugars are going to be even higher, right? So that can be one of the main problems we see with giving steroids. Also going to stimulate protein degradation. So this is not going to be, it's going to be more of a catabolic kind of drug, right? Or a catabolic kind of substance, because it's not leading to further tissue development. If you're in a stress state, I don't necessarily need to make new muscle. I may need to break down that muscle and those amino acids for energy production, right? So you can see over a long period of time protein degradation that happens. This will also stimulate lipolysis. So you end up seeing kind of fat wasting, body wasting that happens there. And also touching on the immune system. So glucocorticoids are very potent anti-inflammatories. We can use that for therapeutic effect. It can also lead to some other issues. So if you think about a patient who has, say for instance, they're on high-dose corticosteroids for a long period of time, say like rheumatoid arthritis, and you're inhibiting the immune system, what are they at risk for developing? Infection, yeah. So secondary infections are a really big risk for giving exogenous steroids, or someone who is just naturally secreting too much, so they have like a tumor or something like that, they can be at risk for infection as well, which can be problematic. So basically what you end up seeing when you have excessive cortisol ends up leading to further obesity. They get kind of this like moon-shaped face that happens there, and also a buffalo-like torso. It's kind of getting this like buffalo hump that happens on the back of the neck there. As I mentioned, usually we're giving hormones, these corticosteroids, primarily to suppress the immune system and inhibit inflammation. That's usually the main two reasons why we're going to be giving it there. So you can see some of the, also it can stimulate hair growth as well. Call this, you guys know what we call this term? You have excessive hair growth where it shouldn't be.
Hirsutism.
Yeah, hirsutism is that term there. There's also this kind of moon face that kind of happens there. Also this buffalo hump. Right, so you can kind of see some altered fat distribution for patients who have either they're secreting too much cortisol on their own, or we're giving them too much corticosteroids exogenously. These purple striae can occur here as well. So, moving on. Next, we're looking at aldosterone in the adrenal gland. Second half. So again, this is mainly coming from the glomerulosa, and it's going to be primarily affecting blood volume and also affecting electrolytes. So aldosterone basically inhibits, works within the kidney, within the actual nephron itself, to increase reabsorption of sodium. holding on to more sodium, and wherever salt goes, water wants to follow it, typically, right? And so you're going to reabsorb more water, and it actually leads to secretion of potassium. Okay, this can be important because we can actually give drugs to inhibit the effects of aldosterone, and that actually will lead to increased potassium levels. So if you ever hear about potassium-sparing diuretics, this is actually one of the things that does is by inhibiting aldosterone effects. But essentially what we're getting is blood volume, blood pressure increases, which can be good in a lot of cases, but you can also see hypokalemia. We mentioned hyperkalemia being too much potassium in the bloodstream. This would be the opposite, too little potassium. Again, we'll get into more detail when we talk about in pharmacology all of the different types of diuretics work. But just know that we're stimulating more salt reabsorption, more water reabsorption. We're getting rid of potassium. Okay, so for instance, if you had a question that came up on an exam, you know, patients who had hyperaldosteronism, they would be more likely to manifest which electrolyte abnormality. You'd have to think, okay, well, they would be potentially hypernatremic, potentially hypokalemic. You know, those would be the main changes that would occur. Okay, think about questions like that. Okay, so again, very similar process here. We don't really see the same kind of withdrawal effects that you would expect to see with like a glucocorticoid. Sometimes we can have patients who have issues to where they actually are not producing enough aldosterone themselves. They can be mineralocorticoid deficient. Either we have one patient who is has hypopituitary. So we have this one patient who comes into Nemours all the time. She comes into the ER. And she goes basically is missing her pituitary gland, and so whenever she gets stressed out, her body can't really respond very well to it because she can't release this ACTH. Okay, that means she can't release enough glucocorticoids. You know, your blood sugar is always out of whack, but she also can't release enough aldosterone, which means she doesn't have enough mineralocorticoid effects, meaning she doesn't have enough intravascular volume. She's basically losing a lot of water within the kidneys, and so she always comes in hypotensive. And that's one of the big things we worry about is when they come in that hypotensive. We try to give them volume back, but they're not really able to hold it within the vasculature very well. So sometimes we have to give them exogenous mineralocorticoids to help them hold on to that volume a little bit better. Right, so we have synthetic ones that we can give that actually have the same activity as aldosterone. It's just a different molecule. So we'll talk about those when we talk about that in pharmacology. Oh yeah, she's on 15 probably different medications. So like you think about like the thyroid gland gets affected, so she's on thyroid replacement, growth hormone replacement, right? On what else? Obviously, she's on kind of baseline medication to help regulate her blood pressure. So she's usually like on hydrocortisone or something similar to that. I think what else? She's had diabetes problems. Just everything you could possibly think of. Because again, the pituitary gland affects so many things downstream that all that gets affected for her, right? So her med list gets super long, and also she's very prone to getting in those stressed out states. If she gets sick, or if she gets stressed out by some kind of emotional stressor, she gets hypotensive, gets hypoglycemic, has to come into the ER and get tanked up and gets admitted. So it's unfortunate, but it's one of those things where it's like you can only do so much to replace that, and it's hard to for you to anticipate those sort of things. Like your body can respond to that thing naturally, right? So if I'm stressing you guys out with this talk for 4 hours straight, you guys can respond to that. Versus her, she couldn't do that, right? Because she's missing that pituitary gland. So anyway. So you've got insufficient cortisol or aldosterone. We call this Addison's disease. JFK was actually a famous Addison's patient. Basically, by having this, you can see things like low blood pressure, weight loss. You also have some hyperpigmentation of the skin that can occur due to this. And then also the salt craving, which makes sense because they're losing too much salt within the kidneys. They can't really respond and hold on to it themselves. So they're going to have that kind of salt water craving that happens there. Also hypoglycemia due to the lack of cortisol. Okay, so looking at stress, who's under it right now? Everyone, probably. Absolutely. So again, just looking at our body, like we need to maintain a pretty careful balance between being in a stress state and a non-stress state. Obviously, this is kind of an evolutionary response. Again, I do believe in evolution, as we covered last time, right? Just kidding. You don't want to be stressed all the time. That leads to all kinds of downstream problems. You have too much glucose around. You're inhibiting your inflammatory system. It's not good. Like we need to maintain some sort of baseline here. So again, we mentioned ACTH increased release will increase glucocorticoid release, and that will also affect other stress hormones as well. So we see more epinephrine, more norepinephrine, because again, those also get released from the adrenal gland, and then the glucocorticoids, right? So those are all going to lead to that or help with that stress response. And we call this a general adaptation syndrome. And it's good for short-term, proper recovery after stress or after an illness or trauma. That's a good thing. But having cortisol around too much does things like inhibit the immune system. So that way you actually don't have over-response of the immune system to an infection or something like that. Like we like to have a good response to the immune system. We don't have to go haywire with it, because otherwise you get in all kinds of problems when you have too much inflammation. So looking at that adaptation strategy, so when you have an alarm reaction that will activate the adrenal glands, it will increase the activity in the medulla, and that will lead to eventually you have that kind of a stage of resistance where you have kind of readjustments in response. So if you're kind of in a chronic stress state, your body kind of adapts to that over time to try to mitigate some of those responses. So it's not kind of a runaway train in that regard. But over time, you can end up exhausting that, exhausting your kind of adaptive responses, and lead to the state of exhaustion, right? And so, like I mentioned, with that patient who comes in frequently, she's not able to have any kind of that stress response, and so she kind of gets exhausted very easily, right? So again, when we are having like one of those kind of stressful responses that stimulates growth of the adrenal glands, you can also end up seeing atrophy of some of the lymphatic tissue, leading to decreased white blood cell production. Because again, these are going to be anti-inflammatory, inhibit the immune system. You can also end up seeing issues with decreased activity of things like prostaglandins, and prostaglandins are really useful for helping to generate the protective coating on the stomach. And so when you have chronic stress, too much glucocorticoids around that inhibits this prostaglandin production and can lead to erosions of the gastric barrier, and it can lead to ulcers, right? So when you hear about someone who's like chronically stressed out, like what do they usually also suffer from? Stomach ulcers, gastric, reflux. You think about GERD, all these kind of symptoms. You think about someone's like stressed out and they're taking a bunch of Tums and all of that. Like that's kind of the same process that's happening here when you're kind of overwhelming those adaptive responses over the long term. I remember, obviously coming from, an American background. I think we're probably a high stress kind of culture in general, right? Probably some people might agree with me. I remember going to St. Lucia for my honeymoon, and over there, like they're basically living on an active volcano, and they say, "Hey, you know what? No pressure, no problem." I was like, "Oh, that's actually a nice way to say it. As long as an active volcano is not ready to erupt in your face, just don't stress out about it." So I was like, "Okay, try to do that a little bit." Also, why I changed jobs. It's much less stressful in the long run, but. So anyway, some of the things you'll see with this general adaptation syndrome, increases in blood pressure, right? So that's not only from the mineralocorticoid effects, but also from the epinephrine and the norepinephrine, increase in heart rate, cardiac output. These are all good things when you need kind of a short-term stress to run away from something like that. Also breathing rate, blood sugar, all those things are going to be going up. But also, this can have negative effects on the CNS as well. So one of the things you can see when you give patients corticosteroids, so glucocorticoids, you can see alterations in mental status, right? So either they become more aggressive, or they're just kind of they seem like they're hangry almost, like they're just not pleasant to be around in a lot of cases. But so you can see decrease in things like logical thinking, concentration. Obviously, the immune system is going to be taking a hit there, so you can lead to secondary infections. We mentioned that bowel function kind of taking a hit as well. Increased risk for things like GERD or gastroesophageal reflux, peptic ulcers, things like that. And also reproductive function. If you imagine, if you're in a really stressed out state, do you necessarily need to worry about producing a new human being? Probably not, right? So it's one of the things I always told my wife, because when we were first trying to get pregnant, I was like, you're stressing yourself out. It's probably also not leading to pregnancy. And she was like, that's stressing me out even more, what you're saying. And I was like, okay, I'm going to shut up now. That's what I learned. So anyone who doesn't have kids yet, any males out there, just keep your mouth shut. If you're asking the question, should I say this? Don't say it. But anyway, so again, a lot of these responses are all coming from either the glucocorticoid effects, mineralocorticoid effects, and you see how they kind of work synergistically with one another, and also the epinephrine, norepi that's being released from there as well. So again, all these things kind of working in concert. And again, if you're thinking about like which substances do you think are working quickly, or the most quickly, steroids or things like epinephrine? Yeah, epinephrine works a lot faster in a lot of cases because they can go and directly activate things like beta receptors and alpha receptors. On the other hand, the steroids take time to work, and that's because they have to go down to the nucleus, they have to change gene transcription, make new proteins or inhibit proteins. That takes time. And so if you think about a patient who has an anaphylactic reaction, right? So say they eat a peanut, all of a sudden their throat starts to swell up. What's the first medication you want to give them? epinephrine, right? We give them EpiPen or something like that because that works very, very quickly. It's going to lead to a lot of the vasoconstriction and all of that helps to deal with that reaction. You also give them steroids, but it takes time for that to work. So that's why we'll give them at the same time, but really the epi is the thing that's kind of saving their life immediately, and then the steroids start to kick in, you know, several hours down the road, and helps to deal with a lot more of that inflammation that happens from that reaction. So you can kind of think about how long it takes for some of these to kick in. Steroids are going to take a little bit longer than something like epinephrine. Okay. So again, other things we can see, so short-term stress response, we mentioned what that would be. So again, we get breakdown of glycogen to release more glucose to go into the bloodstream, increase blood pressure, all that good stuff. So long-term effects we're worried about with like kind of chronically stressed patients. So we're having increased protein degradation as we're trying to convert protein and fats over into energy sources we can utilize, which you talked about. Suppress that immune system. You see issues with electrolytes being affected. So again, if I'm in a really chronically stressed state, I can lose more potassium. That can affect heart function and whatnot. And so this is one of the things we run into, especially with like critical care patients. If you imagine someone who's coming in with septic shock, they have a bloodstream infection, they're very hypotensive, they're in a very stressed state, and a lot of times you can see that's kind of being counterproductive because we want them to have somewhat of a functional immune system, but they're releasing so many steroids and things like that. Their immune system can take a hit, that can lead to electrolyte imbalances, all kinds of problems in the long run. And so really what we're trying to do for them is to get rid of that infection as soon as possible to allow their body to get over that stress and kind of recuperate. But you know, it can be very difficult to kind of manage that with some of these really sick patients. And you can kind of see how both stress can be working very quickly. The sympathetic nervous system is going to be the fastest way for us to get quick changes in that blood pressure and heart rate. But this HPA axis is going to be allowing for us to have a little bit slower effects. Some of these other hormones we haven't talked about exclusively yet, things like renin. I didn't talk about vasopressin too much, but just know that they're all leading to kind of concerted efforts to do the same thing. And we have too much stress, we're going to lead to disease, right? So that's where you can see worsening diabetes, you can see worsening edema for patients who have congestive heart failure, all kinds of problems that ramp up for this. And we can induce this as well when we give things like exogenous corticosteroids, okay? So we can induce this in patients if we're not careful in giving too much of these drugs. So, other illnesses we can potentially see. I'll say increased risk for diabetes can be a problem if you have chronically elevated blood glucose levels, because that can help to kind of wear out the pancreas and your insulin ability to secrete that. Also mentioned things like, you know, just symptoms similar to ADHD. If you're really anxious and you're really freaked out and worried about something, it's hard to concentrate on, say, something like the PowerPoint slides right in front of you. Sometimes just impaired mental status, cognition, and ability to concentrate, things like that. Those are the big things. And then secondary infections are one of the big things we worry about as well, usually kind of more in the short term. And then also because you're having increased heart rate, increased blood pressure, that's putting more strain on the cardiovascular system, risk for heart disease also goes up as well. So again, no pressure, no problem, just trying to relax a little bit. It's probably good for your health in the long run. Here's where we're talking about the stress in the GI tract, how that has an effect here. So normally you'll find that the GI tract is innervated by the parasympathetic nervous system. It's our rest and digest nervous system, as we mentioned. So the vagal activity here is going to be releasing things like acetylcholine on those muscarinic receptors, and that's going to lead to parietal cell hyperplasia. It's going to lead to release of hydrochloric acid, which remains stomach acids. And again, if you don't have things like prostaglandins around to help stimulate this nice mucosal barrier, right? You're going to see degradation in the lining there. Especially, you'll also see that stress inhibits platelet effects. So that also helps to prevent blood clots from actually developing, and that's where you can get ulcers that actually form there, right? And so you can actually have bleeding, perforation, all kinds of bad stuff. You know how you would tell if you were to have an upper GI bleed like this? How does the poop look? Yeah, so like black and tarry. So that kind of tells you like, hey, stomach acid was affecting that blood and actually metabolizing it and breaking it down. So that's how you can tell. So black and tarry stool, you always want to think like upper GI bleed in a lot of cases. Or iron. Iron actually turns your poop black as well. So black poop is not always a bad thing necessarily. Okay, so let's see where I'm at. Let me go a little bit more, and then I'll let you guys go. Okay. So next we'll look at the thyroid glands. Everyone's like, oh, do you know, let's go? And quick. So anyway, the thyroid gland is going to be located just below the larynx, anterior to the trachea. It's going to have 2 lobes on either side, and it's going to be connected by the isthmus here in between these two. It's very, very vascular. That's why kind of removing the thyroid gland can be very difficult because it is so prone to bleeding. Anything the gland is going to do for us? Produces T3 and T4. What does that do for the body though? Like temperature regulation is a good one. Metabolism, blood pressure, heart rate, all kinds of things get affected by this. And so we'll go over the process of actually producing thyroid hormone very quickly. But here you can look to see here's a capillary, here's blood flow coming to the thyroid gland. Here's one of our thyroid cells actually here. So what's the main cation that we need for producing thyroid hormone? I guess it's the anion. Iodine is going to be the big thing we need there, right? So we need to have a little bit in our diet. Roughly 1 milligram a week is needed for normal function. And your thyroid stores up a ton of iodine for later use. So again, you can go a long time without necessarily needing a lot of iodine in your diet, but you need to kind of replenish that over time. And if iodine is going to be present, then we can produce things like T4 and T3. You guys know which one's more active? T3 is the more active form, so we'll see that's actually going to be the much more active form. T4 is a good kind of storage. It's kind of it gets converted over to T3 in the peripheral bloodstream, where it can then be more active. Normally, when we're giving exogenous thyroid hormone, think about your synthroids, we're actually giving T4. So we're giving it in the inactive form, and the body can then convert it over to T3 later on for more active use. Okay. But essentially what's happening is we're getting the iodine being brought into the cells here. You're going to have a conversion over to iodine, right? So, based on a reaction that happens there. And then eventually it's going to get brought in with tyrosine. Tyrosine is going to be one of the main, because again, what does T3 stand for? Yeah, triiodothyronine. So that's actually produced from tyrosine. So that's going to be basically complex of the iodine, and then they can be added together. We'll look at more of that detail in that process in a little bit. But essentially, then they can be released out into the bloodstream, where they can be either utilized immediately, or T4 can be converted to T3 for later use. So typically you're going to see that the majority of thyroid hormone floating around the bloodstream is going to be T4, about 93% of that, and then about 7% is going to be the active T3. So you don't really need a ton of it, but it's good to have a lot of T4 kind of stored up for later use when you need it. You can also end up producing what we call reverse T3, where basically, I'll show you that in a little bit, but basically the molecules kind of got rearranged a little bit, and so this is actually inactive, so it's not really physiologically useful to produce reverse T3. But again, we can usually store a large amount of it in the gland occasionally, especially when we're in a state where we feel like we're not really getting basically store it for later use. So in case you get to a point where you don't have iodine in your diet for a while, you can still have some to release and kind of supplement yourself for a period of time. So even though you may cut out iodine out of the diet, or say you don't have enough TSH around, it can take time for you to actually manifest that because you have a good store of it for later use. Okay, actually I think I'm going to go ahead and let you guys go now. Do you have any questions before I let you guys go? I'm sorry? You will have some iodine stored in there, but you can also have you can also have thyroxine stored in there because it can be bound to the thyroglobulin. It just says thyroid. I would probably supposed to say thyroid hormone. Yeah. Okay. I will see you guys at 2:30.